Most Americans couldn't point to the Ohio River on a map. Yet this single 981-mile channel carries $23 billion in commerce and supplies drinking water to 5 million people through infrastructure finished in 1929. In January 2026, its flow collapsed 95% in 24 hours. What that revealed about the systems built around it is far more dangerous than the drop itself. Stretching nearly 1,000 miles from Pittsburgh to Cairo, the Ohio River is more than a line on a map. It's the engineered backbone of the eastern United States. Its watershed drains parts of 15 states, collecting rain and runoff from as far as New York and Georgia. Every year, this river moves over $23 billion in goods, making it one of the busiest commercial arteries in North America. But the Ohio does not flow freely. For over a century, its course has been sculpted by a chain of locks and dams, a system first authorized by Congress in 1910 and completed in 1929. These structures, built before the Great Depression, transformed a wild, unpredictable waterway into a reliable highway for barge traffic, grain, coal, and steel. The original network included 51 wicket dams and lock chambers, wooden and then concrete, spaced along the river's full 981-mile length. Today, the U.S. Army Corps of Engineers manages 57 lock and dam installations, some of which still rely on infrastructure nearly 100 years old. Each lock holds back a pool of water, maintaining a 9-foot navigation channel that keeps commerce moving even during dry spells. The economic stakes are immense. A single barge on the Ohio can carry as much cargo as 70 semi-trucks, and a typical convoy replaces a line of trucks stretching for miles. The river's engineered stability has shaped the cities, industries, and supply chains that depend on it. But as the system ages, its ability to buffer against drought and sustain modern demand is tested in new ways. What was once a marvel of civil engineering now stands as a fragile gatekeeper for millions, its century-old bones carrying the weight of a region's future. Drought didn't arrive overnight. In 2022, the Ohio River Basin slipped into what the United States Drought Monitor called a severe drought. Rainfall fell 6 to 10% below normal, and river stages dropped by 2 to 3 feet at key gauges. Barges moved lighter loads, and navigation advisories warned of draft reductions up to 30%. By late 2025, the drought had deepened. Extreme conditions gripped the western basin, with precipitation running 12% below average, and U.S. Geological Survey records showing historic low flows at Cincinnati and Louisville. The Middle Ohio River Drought Statement on January 2nd, 2026, noted a rapid fall in discharge, with some pools skimming record lows. Then came the tipping point. On January 15th, 2026, the United States Army Corps of Engineers issued a dead pool advisory for the river near Greenup, Kentucky. The river's flow, which should have been around 400,000 cubic feet per second for midwinter, collapsed to just 20,000 cubic feet per second, a drop to 5% of normal. The difference is staggering. Picture a river that usually moves the equivalent of 70,000 semi-trucks of cargo per day, reduced to a trickle barely enough for a few hundred. At these levels, the lock and dam system loses its ability to maintain navigation channels, and the water's movement slows to a crawl. Hydrologists tracked more than just the falling numbers. Dissolved oxygen levels at Cincinnati dipped below 2 milligrams per liter, far under the 5 milligrams needed to keep fish alive and municipal intakes clear. Satellite images showed exposed sandbars and stagnant stretches, classic signs of a dead pool where water barely moves and pollutants concentrate. The United States Army Corps of Engineers advisory triggered immediate restrictions on navigation and warnings to water utilities across Ohio, Kentucky, and Indiana. What began as a slow-motion drought had, in less than 24 hours, crossed the threshold into a system-wide crisis. 29 water utilities line the Ohio River, each one a lifeline for the cities and towns that depend on this waterway. On a normal day, Cincinnati Waterworks alone draws enough water to fill over 50 Olympic swimming pools every hour. But with the river's volume collapsing by 95%, the control room at Cincinnati Waterworks faced alarms that had only ever been tested in drills. Stacy Greer, the utility's director, watched as the intake screens began to clog with exposed sediment. Suction pressure dropped below safe limits, triggering automatic shutdown warnings. 88% of Cincinnati's population relies on this single source. As the river fell, the utility's emergency protocols kicked in. Backup wells were activated, and calls went out to neighboring systems for intertie support. Cadiz, Ohio, a smaller community upstream, saw its own intake pumps struggle as water levels slid below design thresholds. The city spent nearly $2 million on emergency repairs and tanker deliveries in just the first week. Across the basin, real-time telemetry showed suction alarms blaring at multiple plants, forcing operators to ration output and issue boil water advisories. For 5 million people in the river corridor, the foundation of daily life, including drinking, cooking, and sanitation, was suddenly at risk. These utilities, built to withstand droughts and floods, now faced a crisis no one had fully planned for. The river's engineered reliability had reached its breaking point, and the consequences rippled outward with every hour that the water stayed low. When the Ohio River slows to a crawl, the threat shifts. Instead of a moving current, the river becomes a chain of stagnant pools. Water that once made the journey from Pittsburgh to Cairo in days now lingers for weeks. ORSANCO scientists refer to this as hydraulic residence time. The longer water sits, the more time contaminants have to accumulate. In typical years, a parcel of water passes through a lock pool in 4 days. At 5% of normal flow, that same journey takes nearly a month. This delay creates a perfect environment for blue-green algae, which are cyanobacteria, to bloom. Warm, still water lets microcystin toxins surge, at times reaching levels 10 times above EPA health advisories. During drought, cell counts have spiked from 50,000 to over 200,000 per milliliter. Downstream intakes have recorded microcystin at more than 10 micrograms per liter, far above the federal limit for drinking water. Coal ash ponds and industrial waste sites add another layer of risk. As hydraulic pressure drops, contaminants seep from unlined pits. In 2024, a coal ash leak near Martins Ferry sent lead and arsenic into the river, exceeding EPA chronic exposure limits. Dr. Linda K. Miller of ORSANCO says that every extra day the river stands still, the more time toxins have to accumulate and reach municipal intakes. Obsolete lock and dam parts, steel plates, and corroded seals dating to the 1920s shed metals as water levels fall, turning aging infrastructure into a hidden source of contamination. Pinpointing the cause behind a 95% drop in river volume demands more than headlines or viral videos. Investigators began by assembling a checklist of hard data. 15-minute discharge and stage records from USGS gauges, lock and dam gate logs from the Army Corps of Engineers, and high-resolution satellite imagery from Sentinel-2 and Landsat. These sources reveal not just how fast the river fell, but where the steepest gradients appeared along its 981-mile course. Next came the operational records, gate movement schedules, emergency drawdown orders, and maintenance incident reports, each one a potential clue to whether the collapse was mechanical, operational, or human-triggered. Analysts layered in AIS logs, tracking commercial barge movements and lockages to see if a surge in vessel traffic coincided with the hydraulic dip. Bathymetric surveys, using sonar and LiDAR, translated the raw stage drop into cubic meters lost, giving a volumetric verdict that could be cross-checked against withdrawal permits and industrial telemetry. By overlaying these datasets across a tight 7-day window, the team could reconstruct the event minute by minute, ruling out sensor error and zeroing in on the true mechanism behind the river's sudden disappearance. Within the first 6 hours of the Ohio River's collapse, the numbers told a grim story. Hydraulic models from the 9 largest utilities showed that nearly half the population, about 2.25 million people, would lose access to treated water as intake heads fell below safe limits. For context, that's the equivalent of every tap in a city the size of Houston running dry before sunrise. Backup reserves, designed for short-term outages, could only provide tens of millions of gallons per day, while the real demand across the corridor soared past 200 million gallons. The gap, over 85 million gallons, could not be bridged by existing interties or emergency pipelines. As storage tanks emptied, municipal directors watched as the outage threshold approached. At 45% service loss, boil water advisories went out and tanker trucks rolled in. With each hour, the margin for error shrank. In the control rooms, the question was no longer if the system would fail, but how many hours until the next city on the line went dark. Today, 5 million lives and billions in commerce hinge on a waterway built for a different century. As climate volatility and aging infrastructure collide, the margin for error vanishes. The Ohio is a warning. When one artery fails, the whole system bleeds. What breaks next?